Hello and welcome to this recorded lecture. We are covering Chapter 2, the System Unit, Processing and Memory. There are 6 learning objectives associated with this chapter. You can have your book and follow along as we go through. This lecture is intentionally intended to complement and closely relate to your chapter reading. In class, we will cover material that's not in the book, but this material is a supplement to your book material. The first of our 6 learning objectives is to understand how data and programs are represented in a computer and to be able to identify a few coding systems. How is it represented in a computer, you ask? Well, the answer is ones and zeros. Everything inside a computer is a 1 and a 0. Now, it's not physically a 1 and physically a 0. It's a high or low computer voltage. Like a light switch on a wall that turns a light bulb on or off. Or it might be not using voltage at all. It might be something stored ones and zeros with magnets. If you take 2 magnets and bring them close together, you can tell before they even touch if they're going to attract or repel. So that's a way of knowing a 1 from a 0. In fact, at the end of this lecture, we're going to talk about a variety of computer options for the future. And if you can store ones and zeros and manipulate those ones and zeros, change ones to zeros and zeros to 1 intentionally when you want to, then you can use that method to build a computer. And you think ones and zeros, oh, that's terrible, right? What can you do with a 1 and a 0? Well, actually, you can do a lot. Everything that computers do, they do using ones and zeros. A couple of terms, we use a bit to refer to a single 1 or 0. You get 8 bits together. You get what's called a byte, B-Y-T-E. That gives you 2 to the 8th power, 2 times 2 times 2 times 2 times 2, which gives you 256 different possibilities, which is enough to represent all the keys on your keyboard, uppercase and lowercase, and all the numbers on your keyboard, and all the symbols over your numbers, like Shift 1 is an exclamation point, and Shift 2 is an @ symbol, and so on, and even some non-visible characters. So 256 ends up being a nice size. And 8, because it's a power of 2, 2 times 2 times 2, ends up working really well for the computer. So there's a historical reason why a byte has been the standard unit of measurement as opposed to maybe 7 bits or 9 bits or even 16 bits. 16 is a power of 2, but it's more bits than we need. 8 ends up being a nice, effective unit. And when we talk about storage and computers, we don't really talk about them in terms of how many bits they are. We really measure them in terms of bytes. So we talk about kilobytes and megabytes and gigabytes, terabytes, and all of those bytes that you see there on the bottom of your screen. Kilo means 1,000. You probably know that. Mega, giga, and tera, those 3 you'll be expected to know as well. Mega means million. Tera, T, means trillion. Giga means billion. It's a shame they called it a gigabyte instead of a bigabyte, because they'd used B, biga, for billion instead of G for billion, then it would be super easy and nobody would ever miss those. But M, mega million, T, tera trillion, and giga should have been biga for billion. Now those numbers beyond those, petabyte and exabyte and zettabyte and yottabyte, those are some really massive numbers that you won't ever come across from a personal computing, personal storage. But when you start talking about storing information, the amount of data that Google searches or the amount of data that the NSA is storing about American citizens and phone calls and all of those things on very, very large scales, we need those even larger units. So the computer works on a binary number system. Certainly when it deals with numbers, it uses a binary number system. And it turns out any number you can represent in a decimal system, which is what we're used to, the digits 0 through 9, you can represent the same value in a binary system. It takes more ones and zeros, so the number 512 takes 3 digits. Well, I can represent 512 in binary, but it takes more than 3 ones and zeros. It takes a larger number. But given enough ones and zeros, every number we have in our system can be represented in a binary system. And you say, well, how is that possible? Because that's just fascinating. And a quick overview of that is shown here on this slide, where we take the number 7,216 and we want to convert that into a binary equivalent. Actually, this doesn't show us how to convert a binary equivalent, but it shows us how that's a base 10, a sequence of powers of 10. So 7,216 means 7 thousands, 2 hundreds, 1 10, and 6 ones. Those values, 1,000, 100, 10, 1, are just increasing powers of 10. So when we write any binary number, it's increasing powers of 2. 1, 2, 4, 8, 16, 32, 64, 128, 256, and on as far as we need to go. And because it's a binary system, you can either have 116 or no 16s, 18 or no 8, 14 or no 4. So it's a little more limited in terms of the numbers that we're going to write, but the result, the values, they're all there. So we don't lose anything by representing our numbers in a binary form. What about letters? Well, letters don't have the direct mapping, the mathematical mapping that we do for numbers. So what we do is we use a standard code. We just agree that the symbol 00110000, that byte, is going to represent a 0. And scrolling down to the middle of the screen to the right there, we agree that a capital A is going to be 01000001. It's kind of like Morse code, right? Dot, 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 dash, dash, dash. There's nothing magical about those sequences. That's just, it became the standard for an S and an O and a T and an R. This is the ASCII code standard for everything you see on your keyboard. ASCII is how you pronounce that, ASCII. That stands for American Standard Code for Information Interchange. And the key there is information interchange. Two devices are going to interchange information between them because they're going to be speaking the same language, and even more specifically, they're going to be using the same standard code. So when a keyboard presses an A, the voltages it sends are 01000001, and every device that connects to that keyboard knows that that is the sequence, the byte of information that gets sent when a capital A is pressed. Now, of course, you don't have to know those sequences, but it is a good idea for you to know that there are some standards out there. And ASCII isn't the only standard, right? The capital A there stands for America, and we love America, but we're not the only country on the planet. There's an EBCDIC extended code, and there's even a code larger than that. So IBM, that was their proprietary environment that they used because they were developing their own hardware independently of other hobbyist building machines. So they had their standard before others did, and they stuck with their standard. But the American code and even the IBM EBCDIC code, they are limited in size. If we want to have our machines be able to represent the symbols and the language of every person on the planet and every language that has ever been used on this planet, including languages that are no longer spoken like Latin or something else, then what we want to do is, what we need is an even larger code. So Unicode represents that. It is newer, it is larger, so a capital A is part of the Unicode, but it's not 8 bits long, it's 32 bits long. But having those extra bits gives us the ability to have extra symbols and extra letters. So every letter of every language that's ever been spoken in the history of humanity and ever will be spoken in the future, there's enough space there for us to represent those using Unicode. Graphical data. This is so we can do numbers, we can do letters, we can do graphics. And you may think, well, wait a second, how do I do a picture with just ones and zeros? And the answer is we break the picture up into very small elements called pixels or picture elements, and we specify the color of just that pixel. And when you get enough of those pixels small enough and they each have their own color, the picture kind of emerges together. So you can represent images using ones and zeros, where the ones and zeros represent the color of a given pixel. The more bits that you apply per color, for color per pixel, the richer and more color range you have available to you for your picture. So a common color scheme that gives us lots and lots of color is to use 1 byte per pixel per color, and to have 3 colors, red, green, and blue. So we end up with 24 bits, and you can have even more than that if you want to have even more degrees of shading for red, green, and blue within those, and get all the color combinations that exist. So here's a picture. I can't see it very well. I think it may look a little better in your book. We can see 16-bit versus 256-bit versus 16.8 million colors, which is a 24-bit image, and what we have on there. And what you're talking about there is how many bits are there for each little itsy bitsy teeny tiny picture element or pixel on the screen. The more bits we have, the more gradients or degrees of color are possible per pixel. What about audio? What about video? Can they be done in ones and zeros? And a yes, the answer is yes, yes, yes. Right? Sound can be done because sound is a wave, and you can sample the wave and get the signal where the wave is at any moment in time, and then just represent that value as a number. And we already know how to represent numbers as ones and zeros, right? The binary number system, 1, 2, 4, 8, 16, 32, allows us to represent numbers. What about video? Can we represent video using ones and zeros? Well, we already know how to represent a picture using ones and zero. And a video is simply a still image repeated 32 times a second, or whatever the frame rate is, 48 times a second, whatever frame rate you're using. So it's going to be a lot of data, and in fact, video is very data intensive. If you're watching video on your data plan, you're consuming more data that way than you are reading tweets or even looking at Facebook where you've got static pictures, because a video has 32 frames, which 32 images per second. But it can be done using ones and zeros. Even the instructions that the computer processes, so all the data is ones and zero, but even the instructions, the programs that you run, Microsoft Word, Microsoft Excel, and Photoshop, and any program you're running, your mail browser and your media player, those programs themselves are represented as ones and zeros. You know, it's called a binary language or machine language when you have the ones and zeros. We don't actually work in machine language. We work in something called a programming language, which is higher level and more English-like. But we translate our programming language down to ones and zeros so that the CPU can understand it and execute the program. If you could look inside a computer, everything there, the data, the video, the images, the audio, the text, and the programs themselves are all represented as ones and zeros. So 1 million bytes, what's the prefix for that? Kilobyte, gigabyte, megabyte. And the answer is megabyte, letter C, right? M for mega, T teratrillion, M mega million, and B billion should have been, is gigabyte, should have been bigabyte. True or false? An MP3 file is stored as ones and zeros. That's absolutely true. Everything inside the computer is stored as ones and zeros. And finally, on our little quick quiz here, the binary number system is what computers use to perform mathematical calculations. And without getting into it, for our class, just like we do basic addition and subtraction using our decimal system, you can actually do the same thing with ones and zeros, and it behaves exactly the same way with carries and subtractions and borrowing, when all those factors work in a binary system the same way they work in our system. Okay, learning objective 2. Inside the case, there's a number of elements, a CPU, memory, buses, and all these things. What do we see inside the case? Well, our system unit is what we think about when we think about a standard desktop computer. Right? And if we open that case up, you'll see a number of components. You'll see a motherboard, you'll see a fan on top of a CPU to keep the CPU cool, you'll see a power supply, and in the second part of this chapter 2, we look at the elements inside of our system unit. So in this figure, this is a drawing, obviously not a photo, but in this drawing, we see a system unit, case has been removed, and you look inside of it and you can see the motherboard, which is the green flat circuit board at the bottom, and things are sitting on it or near it, including, I don't know if my mouse is going to work here, but including the CPU, and the CPU right now is under something called the fan because it's going to cool everything. There's a great big power supply that allows you to take the voltage from your wall and turn it down to the 12 volts or whatever volts you need to run all the computer equipment. Here we have little slots where memory plugs in, our RAM memory, which is very close to the CPU. That's intentional because the CPU and memory, as we will see, are the two primary hardware devices for processing, and they're very, very, very fast. So they're faster than anything else on our computer, and we want them to work together and minimize the distance between those. You have these little expansion slots where you can plug in a network card, or you can plug in a video card, or you can plug in a high-end audio card, or you can plug in something else that you want to have on there. We have little slots up here where you can add a CD burner, or you can add a second hard drive, or some different things that you want to have. Right? So this is what we're talking about in this second part of chapter 2. So just a few terms. A computer chip means a piece of silicon that has some transistors which are able to hold ones and zeros and switch ones from zeros and zeros for one built onto the chip. Circuit board is the board that has the chips on them. The motherboard is the great big circuit board that fits inside your system unit that everything plugs into the motherboard. External devices are things outside the system unit. So if you plug in your keyboard, you plug in your monitor, you plug in a local network, anything you're going to plug in, you plug in your camera to download videos from your camera. Anything that's outside that system unit is an external device. Wireless devices are outside the system unit, so they're external devices, but you don't have to plug them in. They are connected using Bluetooth or some other technology. The power supply is inside the motherboard, inside the system unit. It provides power to the motherboard, and it comes with the system unit case. When you buy the case, the power supply comes with that. It doesn't have to, but it usually does. Now, of the hardware inside the system unit that plugs into the motherboard, the CPU or the processor, that's your main thing. That's the most expensive piece of hardware. The CPU is called the brains of the computer, and we're going to talk about CPUs in this chapter right now, and then we're going to come back and talk about them even more again later in this chapter. So this is, and for good reason, because of all the hardware, the CPU is the most interesting piece of hardware, and it's the most expensive, and it's the fastest, and it's the most important. CPU is sometimes called the brains of the computer because it's where the logic happens. It's where the processing. If you add two numbers, 2 plus 2 and get 4, the CPU does that. And only the CPU knows how to do 2 plus 2 equals 4, and only the CPU knows how to do a logical comparison that says that 5 is greater than 3. And the CPU is able to do those comparisons, so it's called the brain. It is a chip. It's produced by IBM and Motorola are the two companies that make most of the CPU chips inside of most computers. And even though we're talking about system units right now, realize this also talks about your phone, a tablet, smaller computing devices that don't have a great big system unit. They still have a CPU. They still have memory. They still have all the things that we're going to talk about, or most of the things we're going to talk about. This is not limited to, these terms we're describing here are not limited to a big system unit. They also apply to your notebook, they apply to your laptop, they apply to your smartphone, and they apply to great big computers that Google uses to do billions of searches a second. The CPU can actually, to improve performance, and again, improving performance and how the CPU works with memory is what we're going to talk about. We're going to revisit this topic, but we'll go ahead, our authors go ahead and explain early that the CPU can actually have some redundancy built into it. You can have 2 cores where each core is able to do its own processing. You can have on the same chip, something the size of your thumbnail or not much bigger, 2 cores or 4 cores, which would be called quad core, and they're making these chips now that might be a little bigger than your thumb. They might be an inch by an inch, but they've got 64 cores or even 90 cores or so, which is really pretty impressive. If we look at the processor, you'll see that it's on a chip that's bigger than your thumbnail, but a lot of that chip is just the housing with all the little connector pins on it so that it plugs into the motherboard. The actual chip where the logic and the core hardware exist is pretty small. Even in that figure there, you can see that there's 4 cores on that chip that's being shown, and those cores and the cache memory built onto the CPU chip, that's maybe less than half of the entire chip, right? If you measure the chip, it's 1.5 inches by 1.5 inches or whatever it would end up being. But the core is a much smaller part of that. And there are numbers out there, and you can see on this screenshot how many cores there are for an Intel Xeon chip and a i7 chip and all of those. Those numbers change over time. Computers are getting faster and faster, cheaper and cheaper, smaller and smaller. But just for you to get an idea of some of those numbers. Also, look at the clock speed. It has a GH following that. That's gigahertz. Remember, giga means bigga for billion. So we're talking about multiple billions of hertz, cycles per second, that these processors are able to do. In 1 second, from now till now, in that 1 second, these CPUs are able to do 2, 3, 4 billion cycles per second, which is really, really pretty impressive. And we're going to talk about that. We're going to revisit CPUs. CPU clock speeds is what I was just talking about. They are measured in gigahertz. Really, the CPU clock runs at megahertz because everything else on the motherboard runs at a slower speed, but the CPU itself, for every clock of the tick, which is kind of like a drum beat that everybody listens to on the old, if you've seen a movie where they have the old boats where people are rowing in unison, there's a guy beating a drum, boom, 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 and everybody's rowing in unison. That's kind of the way the motherboard works, as a very bad analogy. It's kind of the way the motherboard works because everything on the motherboard, the memory and the CPU and the network card and the video card and everything else, they all sync up in terms of doing their actions to the clock on the motherboard. But the CPU, every time the drum beats, it goes off and runs like 10 instructions. And then the drum beats again, and it goes off and runs the next 10 instructions because it's actually running at a significantly higher speed than everything else. The word size refers to the standard unit per processor. And again, these are both powers of 2. Right? Just like we said that a byte is 8 bits because 8's a power of 2. 32 and 64 are also powers of 2. 2, 4, 8, 16, 32, 64. And that's the standard unit. That's the size that the processor works with. When it gets the next instruction or the next piece of data from an audio file or the next piece of video from a video file or whatever it is, it's working in standard units. And having that larger word size gives you more power. Even if you don't have, even if it's not going faster, you're swinging a heavier stick, so you're able to do more damage. And one of the advantages of 64-bit operating systems and 64-bit computers, which are becoming the standard if they're not already the standard, is that when it comes to accessing memory, you have to reference the memory address, and 64 bits allows you to have more memory that you can access. With the old 32-bit operating systems, you were limited in how much storage you could reference. And as storage has gotten smaller and smaller and cheaper and faster, the need to have 32-bit architecture to take full advantage of all the memory that's available, that's been one of the advantages of it. And cache memory, when we talk about storage, particularly in Chapter 3, we'll say more about cache memory, but the idea of cache memory is it's temporary volatile memory right there on the CPU or right between the CPU and memory. So as the CPU and memory share information, cache is kind of the buffer between those two. Now, memory, this is our second biggest element on our board, and we are going to speed up a little bit here. We're not going to go in huge detail on each element, but the CPU deserves some time and attention because it's the most expensive and most important piece of hardware. And memory deserves some time and attention because it's the second most expensive, second fastest, and second most important piece of hardware on our motherboard. Memory is where the data, the programs, everything gets stored that the CPU can have access to. The CPU can't actually talk to your hard drive. The CPU can only see and talk to memory. So if you've got a file that you want to run, you have to load that file from your hard drive into memory so that the CPU can then get it and do its CPU stuff to it. RAM memory is volatile. I think it said on the previous slide, when you turn it off, you lose the power, you lose the information in RAM. That's why we store our files. We've probably all done that at least once. Had a file that did not get saved and the machine got turned off and you lost your work. Part of the reason it's done that way, that it's volatile and requires electricity, is because electricity is pretty fast, right? Electrons are small and they move at the speed of light. So when you're turning on a switch, you can immediately get that 0 to a 1 or 1 to a 0. The downside is you've got to save your work because once you turn off the power, you're going to lose what's in there. Memory comes in these sticks like we see on this diagram, and those memory sticks plug directly into the motherboard, close to the CPU, and they're able to share information. When we think about memory, you can think about it like mailboxes. That I have a mailbox for my home, and I can go out to my mailbox and I can see what's in there. I don't look in other people's mailboxes, but they've got their own mailboxes. If I want to send a letter to a friend, I know their address and I can send them a letter. If they want to send a letter to me, they can send it to me. That's kind of an analogy for what happens with memory, that there are specific addresses, and if you want to put a value somewhere or get a value from somewhere, you know where it is. Another analogy that's used sometimes are seats in an auditorium and assigned seats. So if you want to give somebody a message, you know exactly where they're sitting and you can get that to them and they can use it another way. So memory has assigned addresses, assigned mailboxes, assigned seats. So we can talk about what's in memory at a very specific location and get what's going on there. So memory, if we think about it hierarchically, the CPU has its own memory, something called registers. When you add two numbers, 3 plus 5 to get 8, those values 3 and 5, they have to be in a register, and the resulting value is in a register. Cache is that buffer between the CPU and main memory. Cache memory is a go-between, and there's actually levels of cache. There's L1 cache, which is actually on the CPU, and there's L2 cache, which is typically not on the CPU, but it's on directly on the motherboard between the CPU and where the memory exists. And these levels of cache, as they get bigger in size and slightly slower in performance, and it scales up to until you get to the memory, which is bigger in size. There's more memory than cache on your computer, but the memory performance is slower than the cache. Then we have non-volatile memory. This is memory that is designed and engineered in such a way that when you turn off the power, it does not lose its electricity. And this is kind of a cool area of computing technology that is growing. At some point in the near future, this is going to be our main memory is probably going to be non-volatile, which means you can be working on a paper and the power goes out and you turn it back on, 2 hours later when the power comes back on, and you haven't lost anything. We're not there yet to where we can use large amounts of non-volatile flash memory, but we're moving that direction. We do store some information on the motherboard in non-volatile flash memory on something called ROM, R-O-M, read-only memory. You can see ROM there on the slide. And the purpose of this ROM memory helps us with, well, when you first turn on the computer, what does it do? If all of its instructions are in volatile memory, how does it know how to boot up? How does it know how to turn on the monitor? And the ROM allows us to do that. Our motherboard, some computers have GPUs, which are graphical processing units. They're designed like CPUs, but they're optimized for dealing with graphics, floating point calculations, which are very frequently used in graphical calculations, and so on. So a GPU that's specific to graphic functions can be part of our system as well. The CPU runs fast and it runs hot. So you will see some sort of a heat sink, heat dissipation, fan, cooling device of some form will exist on your CPU and possibly on other elements. Your GPU, your graphics card, very well could have a fan and cooling things off because the graphics element is also going to be very hot. And heat sinks have a lot of surface area using metals that conduct the heat very quickly, so you can draw the heat off of the processor and pull it into the case, and the case itself often has a fan to take that hot air out of the case and dissipate it into the room, all for the purpose of keeping our CPU and our GPUs cool. There are liquid systems, there are immersion systems. People who are into graphics and gaming might be familiar with some of these because that's part of what's going on. Your very high-end graphics cards run very, very hot, and they've got some very elaborate cooling systems. Now, if you've got a notebook and an ultra-thin notebook, you don't have room for a big fan, so they just have to design, part of the goal of designing those very small computers is trying to make them to where they don't use a lot of electricity, to where they're not generating a lot of heat, so that they can cool just using simple airflow and not having elaborate cooling systems. Here we see some figures from our book about cooling systems. The figure on the right, if you look at it, it's a cooling fan as a platform on which your laptop can stand. Really important if you're using a laptop that you don't block the air intakes. You can ruin and destroy your laptop if you've got it sitting on your bed, sitting on the comforter on your bed, and it kind of mushes down into the comforter on your bed, and the little air vents on the bottom of your laptop where air is supposed to flow to keep the CPU cool, if you block those, then you can overheat your laptop and destroy it. So be mindful of that. Device, like you see on the picture on the right, gives you a hard surface. There's actually a curvature in there to help airflow, and there's even a fan to keep that air moving more frequently. If you've got a very fast, hot running CPU, you might want a device like that. Inside our system unit, we're still talking about our system unit and all the cool things that are in the motherboard and connect to the motherboard. There are these expansion slots where you can plug in a video card, you can plug in an audio card, you can plug in a network card. So all those can be plugged in as part of our motherboard. Here we see some figures of some different cards. There's a network card and a USB on the right. That doesn't plug into the motherboard, but it plugs into the unit through a separate port. There are ways of, these are just ways of increasing the functionality or the storage or the capability of our unit beyond what's already inside the system unit. Now, all these different devices have to be able to communicate and share information with each other. How do we do that? Buses. Buses are electronic pathways. If you've ever looked at a circuit board, if you've ever opened up your computer or your cell phone, or opened up any device that had a toaster, any device that had a circuit board inside of it, you'll see that the board itself has these little lines that run parallel on the board. Those are called buses, and those are little electronic pathways that ones and zeros can pass along. And the buses can be 8-bit or 16-bit or 32-bit or 64-bit, depending on the information that's being passed along those lines. Of our buses, there are multiple buses on our motherboard, right? We know we have to have the CPU and we have memory, and it's got its own bus called the memory bus. There's also the front side bus, right, which is where the CPU connects to the chipset that controls everything else on the board. So the memory bus and the front side bus, those are the two buses that have CPU that end up communicating to the CPU. And you've got other buses that are less important in terms of the functionality of your system. PCI Express and universal serial buses and FireWire buses. And these are ways that we take our keyboards and our monitors and our cameras and connect them into the system unit. But we don't do that often enough that they become mission critical. The CPU is mission critical, and the performance of it always matters. Okay, quick quiz number 2. What type of memory is erased when the power goes out? RAM memory is erased. Our main memory is called RAM memory, and power goes out, we lose what's in RAM. True or false? The CPU can also be called the motherboard. That's false. The CPU is one of the many components on the motherboard, but the motherboard and the CPU are very different things. Question 3, an electronic path on which data travels is a bus. Learning objective number 3. The beautiful thing about this, you can pause and come back if you want to. You can also be flipping through your book and following along. So if you've still got the energy, let's keep going. This is good stuff. Describe how peripheral devices or other hardware can be added to a computer. This is the most obvious thing in this chapter, I think, is this section about ports and connectors. But we'll still go ahead and define some terms here. You've used them before, but you may not have known what they're called. Port, this is the name that we give to the place on the system unit where you plug things in. So the USB is a port you can plug in. The monitor plugs into a video card. This is all these slots and open spots are called ports. And connectors are the term for the part that plugs in. So when you hook up your camera, if it doesn't have Bluetooth or ability to connect without a physical connection, you're going to have some kind of a cable that's going to connect from your phone to your system unit. And that cable is going to have a connector on the end of it, and that connector is going to plug into a port on your system unit. And once you've made that connection, ones and zeros can transfer and the images can be downloaded or whatever we're doing there. Some of the more common connectors, monitors have their unique connectors. HDMI is the new standard, but you'll still see some computers that have the older VGA connections. USB is kind of a standard connection. Keyboard, mouse, printer, a number of things can connect that way. Network connectors use this, something called an RG45 connector that they will connect to the internet if you're connecting wired versus wirelessly. Audio ports, and so ports and connectors. You have those on not just your desktop unit, but you have them on your phone, on your tablet, on your notebook and laptop computers. They all have these ports and connectors. We can see them here on a laptop and on a tablet, the same idea. Ports where you plug things in, connectors connect to the ports. Now, number 4, understand how a computer's CPU and memory components process program data instruction. So I mentioned that we were talking about the CPU and memory before, and we were going to come back to it. Well, now we're coming back to it. The CPU and memory work together. They are like a buddy team because the CPU is what does the logic. It knows how to add 3 plus 5 and get 8. It knows that 3 is greater than less than 4. So it can do math and it can do logic. But it's limited in how much information it has. It has a handful of registers, it has some level 1 cache, and you need a lot of ones and zeros to do your processing. So that information is stored in RAM, and the CPU gets the information from RAM, does its processing, and stores its results back in RAM. It's a big process here. So as a refresher, the CPU is the brains of the computer, and the CPU over the last 4 or 5 decades, have gotten smaller and smaller, cheaper and cheaper, and faster because of this thing called Moore's Law. It's not because of Moore's Law, but Moore's Law is the observation that the process of producing chips, the physical manufacturing process, they're able to improve that process on a regular basis to the point that every 18 months to 2 years, you're able to get twice as many chips, twice as many transistors, the electronic devices, the physical devices that store the ones and zeros and transform them from ones to zeros and zeros back to ones. You're able to get twice as many of those on the same square inch or the same square centimeter or whatever it is of surface area. It's able to get denser and denser and denser, doubling every 18 months to 2 years. So that has had a big impact, and today's CPUs are significantly more powerful than what we had in the 60s and the 70s and even in the the 50s when they were doing our early computers. On a single CPU, we have a number of components. The most important are the ALU and the FPU. The ALU is for arithmetic logic. So really, that's even the most important. It does have an element for doing special floating point computations. I mentioned that floating point computations are important for graphics, and that's why GPUs, graphical processing units, they have an emphasis on GPU. There's control unit and a prefetch unit and a decode unit, and the registers and internal cache and the bus unit. And this is what a CPU looks like at a high level overview. There's in the lower left hand corner the bus interface. Remember, buses are data pathways, so there's a way for data to come into the chip to be processed, and there's a way for the data to go out of the chip to be processed. Registers are the high-speed storage locations within the CPU. When you want to add 3 plus 5 and get 8, you have to store those values 3 and 5 in registers, and the results are also going to be stored in a register. The ALU and the FPU, ALU stands for Arithmetic Logic Unit. This is where you have the hardware that knows how to add. And this is where you have the hardware that knows how to take two numbers and compare them logically to say, are these the same or are they different? Is one bigger than the other? Yes or no. So you answer yes or no questions with the logic unit. You do basic math with the arithmetic part of the ALU. And amazingly, simple math and simple logic is all you need to do the machines, to do everything that computers do. And the other things there, You can read about them, but I don't want to go into too much detail on them. I'm not going to expect you to know this material 5 years from now. Just know that there's no magic wands, there's no Harry Potter, there's no Dumbledore, there's no Doctor Strange, right? It is straightforward, scientific, A equals B equals C performance. But it has to be detailed and spelled out. So the control unit, the prefetch unit, decode unit, and internal cache, those do all those things. The system clock. Remember, the system clock is what is the drummer, boom, 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 and everybody's rowing in sequence. And every time the drum beats, boom, everything on the system board, everything on the motherboard does its next step, with the exception of the CPU, because every time the drum beats, boom, the CPU goes off and does 10 instructions. So it's performing even faster than the system clock. And there it talks some more about that. So a system clock running at 200 megahertz, you add a 0 to that, you get 2000 megahertz or 2 gigahertz. That's how fast the CPU is running. So what does the CPU doing? Remember, the CPU and memory work together, and that is something called a machine cycle. And if you look at this machine cycle, you'll see step 1 in the upper right hand corner, fetch, and step 2, decode, and step 3, execute, and step 4, store. And that process is repeated billions of times per second. Fetch, get the instruction. Decode, look at the instruction. Execute, do what the instruction says, and then save the results. Get the next instruction, look at it, do it, save the results. Get the next instruction, look at it, do it, save the results. Get the next instruction, look at it, do it, save the results. So that machine cycle is a way that the computer does its processing. And it's an interesting thing that you can do with your hardware, because it's separate hardware that gets the instruction, it's separate hardware that looks at the instruction, it's separate hardware that does the instruction, and separate hardware that stores the instruction, because the computer has special hardware, the CPU has special hardware to do everything that the computer does, that the CPU does. So you might think that those 4 steps, fetch, decode, execute, store, have to, they can happen by themselves. But what you can do is you can use your hardware more effectively, where you fetch the first instruction, and then the fetch hardware, instead of it just sitting and waiting for that entire instruction to finish and then fetching the next one, you can go ahead and at the next time moment, go ahead and fetch the next instruction. So what this figure is showing is column 1 is second 1. And it's really not even a second, it's much faster than that, right? So time unit 1, and then column 2 here is time unit 2, and column 3 and column 4 and so on. And in the top figure, we see it takes fetch, decode, execute, store for green, instruction 1. And then it takes another series of clock cycles to fetch, decode, execute, and then we would have store for instruction 2 if our figure continued on to the right, fetch, decode, execute, store for figure 3, and so on. But at the bottom, we're using this process called pipelining. And this is kind of a cool, elegant idea. So we fetch the first instruction, and then in the next time cycle, that first instruction in green has been fetched. It's now being decoded. Well, the fetch hardware, it has nothing to do. So it goes off and fetches the next instruction. And the next time cycle, first instruction is now being executed, the second instruction is being decoded, and again, the fetch hardware is free. It can fetch the third instruction and fetch the fourth instruction in the fourth time cycle, and the fifth instruction the fifth time cycle, and so on. And by pipelining in this way, you're able to get a significantly higher throughput. Now, it's not perfect. If it was just this simple, you would get 4 times the performance. And in reality, pipelining doesn't give you 4 times the performance for a number of reasons, not the least of which is you're not always fetching the right instruction. Sometimes there's a reason you have to jump or branch and fetch a different instruction. But you do see significant performance, maybe double or more, when you use this pipelining approach. And what's cool about this is it's not that you have to add any new hardware, you're just changing the way you control the hardware. And that's a neat engineering feat that they did there. All right. Number 5, learn to evaluate several strategies that can be used today for speeding up the operations of a computer. So how do we make our computers faster? You've got a computer somewhere, a laptop, a desktop, somewhere you've got your hands on a computer. What are some things you can do to make it better? Well, adding memory. If you don't have enough memory on your machine, then adding memory can improve the performance. So especially if you have 2 or 3 or 4 or 5, 6 programs open, and as you open more programs, you see your performance start to degrade, start to slow down, and that's a pretty good sign that you might want to have more memory. And replacing memory is not that bad of a deal. You can actually YouTube, upgrade my memory, and you can see some videos on how straightforward it is to do that, especially on the big desktop units where you can get into it easier. It's a little harder on, it might be harder on some laptops, especially the very, very narrow laptops. But you can replace your memory. You can order your memory for $100 or so. You can get more memory for a computer, and that can be something to improve your performance. You can defragment your hard drive. If your hard drive is 80% and 90% full and you're trying to save files there, it's going to slow things down. So you can do something called a defrag, where you take the files that have been spread out in small pieces over your computer and bring them together and use your space more efficiently. That will help speed things up. You can get an extra hard drive. That will help speed things up. Again, if you're near capacity on your existing hard drive, things are going to slow down. Having an extra hard drive is going to make it easier to read and write from your hard drive. Upgrade your video card if you're using video, and so on. There are some things that you can do to improve the performance of your computer. Now, the really interesting thing, though, is because computers are getting faster and faster, cheaper, cheaper, smaller, every couple of years, it almost gets to the point, well, it's almost easier to buy a new computer than to upgrade a 5-year-old or 6-year-old or 7-year-old computer. But for a semi-recent computer, maybe just upgrading the memory, maybe just upgrading the hard drive, maybe just defragmenting the hard drive. There are some things that you can do to improve your performance. And finally, in our lecture here, what are some processing technologies that may be used in the future? Now, predicting the future is very difficult, but we know some things about our future performance. This figure, I think this should have been on our previous slide, I'm sorry. Some more things you can do fixing your computer. Uninstall programs that you're not using, delete temporary files, get the dust out. So I think that was, yeah, I'm sorry, these slides are still talking about things you can do to help your computer, getting an extra hard drive, adding more memory. Okay, so now we start talking about, well, how do we do in the future? What do we do in the future? Well, there are a number of things. Making CPUs faster will make computers faster. Having more cores, that is redundant hardware on the CPU, so that you can have tasks being done one chip, but 72 cores or 24 cores on a chip can improve performance. Virtualization allows you to use what looks like a Mac, or what looks like a Windows machine, or what looks like a Unix machine, or what looks like some other operating system, some other functionality. It looks like a bigger machine. You can do that virtually. So there are some things going on. We can improve the materials that we're using. And again, we're talking about not you as your personal machine at this point. We're talking about people building the machines and researching the machines. What are they doing? Like, there are people that are working on flexible components. Would be really nice about this, it can fit into your clothing. So you're going to have a smart t-shirt or a smart jacket in the future, because it's going to have material that is flexible, but it's still able to represent and manipulate ones and zeros. And when you can represent and manipulate ones and zeros, you can do interesting computing things with that. We already talked about pipelining, but I think our book talks about it again here, or maybe this is where the book actually talked about it. But we've discussed that, so I'm not going to repeat that in my lecture right now. You can go back to 15 minutes ago or so where we talked about it. We've talked about the fact that there are multiple cores per processor, and you can also take multiple processors with multiple cores and hook them up together. This is when we start getting to these supercomputers. Right? So the Titan computer shown at the bottom of the screen there is located in Tennessee, and where they were doing work, I think, during World War II, the facility where they did some atomic bomb research in Tennessee during World War II. That place is still a research facility, and they have a supercomputer there called the Titan. And that supercomputer has 18,688 nodes inside 200 cabinets. So there you're seeing the cabinets, and those cabinets are about the size of a person. I think those are 5 or 6 feet tall, each of those little cabins there. And inside each cabin, there are 24 blades per cabinet and 4 nodes per blade. Right? So you would, I don't have a good figure of a blade there, but it's the size of a pizza box, basically, that you can pull out of the cabinet and put into the cabinet, and 4 nodes per blade. And each node itself is a 16-core processor with 32 gigabytes of RAM and some GPU processing elements on it with its own memory. And basically what that means, you put that all together, you've got a single computing device that has the equivalent of almost 300,000 processing cores and almost 700 terabytes of CPU and GPU memory. So it's a massively powerful big machine that's just taking advantage of having multiple machines working in parallel together. And why would you build something huge like that? Certainly not to surf the web, certainly not to write Microsoft Word projects, but if you're wanting to simulate weather, if you're wanting to simulate nuclear weapon testing, if you're wanting to project solar activity and star alignments and these things, there are times that you have just raw computational tasks and you want to have these super powerful machines to do those. Okay. So here we go. Still talking about the future, nanotechnology. This is something from our book about the future. The idea that we can have, we can build things from the molecular level up. Right? Traditional manufacturing is taking raw materials and putting them together. But at a molecular level, what if we actually modified the atoms? That's the idea behind nanotechnology, dealing with very, very small, the scale 100 nanometers is the standard size that says you're dealing with nanotechnology. But interesting things are being built and are occurring at this very small scale that have nothing to do with computers. But one of the interesting things being done at the nanoscale is how do we do computing activities there. Some non-computing nanoscale technology, you can talk about the space elevator. If you want to YouTube the space elevator, Google it right now, you will find it's kind of fascinatingly cool. And usually those space elevator concepts involve the very, very strong, very, very small and light technology that is only made possible through nanotechnology research. Quantum computers is in our list of future trends. The idea behind quantum physics is that there is some uncertainty involved at a fundamental level. That you can know, for example, where an electron is or how fast it's moving, but you can't know both. And as soon as you measure one, then you don't know the other. The idea of Schrodinger's cat you may have heard of before, because of this fundamental uncertainty that exists at a quantum level, that the cat is alive or dead in the box, and you don't know until you open the box. Taking that uncertainty, instead of having just a 1 or a 0, using the uncertainty of quantum bits, the value is both a 1 and a 0 at the same time, and only upon later reflection does it fall into one of those two states. That allows for some interesting computational activities, especially in things like code breaking. So if we ever get a quantum computer built, it will be able to decrypt messages that currently can't be decrypted even with supercomputing technology. So it's a really interesting theoretical environment, theoretical in the sense that it doesn't exist today, but there are principles behind why they're building those and how they hope to have success with those. Optical computing, The idea here is that we're going to use light to represent ones and zeros, right? The light can be on or off, and if we can represent ones and zeros using light and manipulate those, design our systems that way, we can have computing devices that use that technology rather than magnetic technology or rather than traditional transistor technology. At some point, Moore's law is going to run out, probably in the next 15 years or so. So these devices, quantum computing and optical computing, these approaches are being explored as what might happen next. Terascale computing is just referring to tera as in trillion. So we're talking about trillion calculations per second. And we already have computers heading in this direction. The supercomputer we talked about in Tennessee is way more than higher scale than this. So terascale computing is something on a smaller scale that a business might use, and a form of computing. But because of the parallel processing and multiple cores, the idea that you might have a single chip at some point in the future that has terascale features associated with it. 3D chips. This is also getting to the idea of Moore's law makes it harder. Things are getting smaller and smaller, faster and faster. But at some point, you're getting down to that nanoscale, microscale, and you can't get any smaller until the electrons start literally bumping into each other. So what might happen, instead of getting smaller on a flat surface, you might start going in 3 dimensions. So we're growing up as well as out. And we can build, or researchers are looking at ways, can they build a CPU that has 3 dimensions, and it's kind of a cool research project that they're working on. So our last quiz here, optical computers use which of the following to transmit and process data? They use B, light for that, optical light. True, false. If your computer is running slowly, adding more memory might speed it up. That is true, especially if your performance gets worse as you have 2 or 3 or 4 or more programs open. You know, it starts off fine when you first boot it up, but once you get a couple of programs growing, it really slows down. Then you know that adding memory could improve your performance significantly. And a quantum bit is called a qubit. That's how it's pronounced. That was on the slide, but I didn't mention it. And the idea behind a quantum bit is that it's not a 1 or a 0, but it's both. And it's in an indeterminate state, and it's able to look at all the possibilities for that state and come back and process it later. Very, very helpful for code breaking. Okay, there you go. You've got your chapter, and hopefully this video helped as you kind of flip through the chapter and see the highlights of the material. Have a good day.